So let's start our last truly lecture of the class. Next week we'll have just a demo of our exam. So welcome and thank you for being here. I think it's -2 degrees outside, so I appreciate that you take the time and the effort to come here. So today is, let's say, a potpourri or a mix of things that are left at the end and are not really strictly linked to the flow of the lecture that we have been doing through the semester. But they are important topics, and I think we should at least touch it a little bit so you have an idea of that this exists, and if you know them, it's just a refreshment for you. So we're going to go slightly on MonteCarlo simulation, which is another way of approaching statistics or data. Then we talk about random walk because it's something related to, in some way, probability, right? And sample size estimation is a very important topic that could be a lecture itself, and that is not really well defined in some aspects, but there are some ways of estimating how many samples you need, how many data points you need to be sure that what you are saying is true, or at least that it has high chances of being true. And the last topic will be error calculation, which we approach it from a stochastic point of view, not from mistake, let's say. So, but let's go for the lecture today. So, to motivate MonteCarlo simulation, I have here, I always say this thing, I have here the way that we have seen data, or how we have analyzed data, or trying to analyze data in this class. And it's the, let's say, the classical way of doing statistics. And so you have a bunch of data, so you have collected, you have made an experiment, or you have recorded data in some way, and then the first thing that you try to do, you try to describe the data, right? So we do, for example, we take the mean or the median of the different groups, then we see how much this data is dispersed, right? The standard deviation, variance, or whatever. Then we, for example, try to fit a distribution, so we want to see how the data is distributed, or not, or we want to compare them. So that's kind of the descriptive part of the analysis. Then you want to get to your inferential part, where you want to infer from the data. You just took a portion of the population, and you want to see, for example, this population is larger than the other population, for example, in some parameters, in some measurements, right? So then you do, for example, you try to fit the distribution, then you compare the distributions, you compare the means, we do hypothesis testing, and all these things that we have seen so far. So that's one way of doing the analysis. The other way would be to, instead of start with the data, Ulam and Newman, so for Newman, thought about starting with some guesses already of how this data is built into, right? So they say, why we don't think about, for example, some physical parameters that if you combine them, it will give you the data that you actually are collecting, right? So the idea is to first to define some parameters, some distribution of this parameter, and then you combine it in some way, and then you get some result. And you compare this result with your data that you have. If they match, probably this parameter are governing this phenomenon, right? So I'm not sure how this is not working today, but okay. So you model this, and you model, you combine them, and then you do simulation. So you simulate this parameter in different conditions with different possibilities, and at the end you compare your data with the data that's outcoming from this model, and then if they are similar, you can say, well, these parameters probably are the cause of this event to happen. If it's very off, then you say, well, probably it's not. Okay? So that's pretty much the idea of MonteCarlo simulation, or the motivation for for using Monte Carlo simulation. The problem with Monte Carlo simulation is that you will have to use random numbers. So you need to have a big amount of random conditions, and for that you have to create a long string of random numbers. And I think we have talked about this in a lecture. That is not possible to do that with computers, for example, because what you get is something like deterministic random numbers, let's say. So if you take MATLAB, for example, you run the run D or the run N function for a short string, and you say, I want to have random numbers from 1 to 100, and you take 10 of them, they will look quite random. But if you take millions, then you will start to see some patterns in this random number. So it's not really a true randomization of the data, but it's something there. So that's a weakness of the problem of Monte Carlo simulation. There are truly randomness or non-deterministic randomness in nature, in physical phenomena, and yeah, for example, here I put an example of a resistor in an amplifier. So the resistor, the physics of the resistor will create noise that is truly random. Okay, so that would be a really random data. But we take that, we get as much as we can get from the computer, and we run the simulations. So, as always, it's good to have an example to see how, for example, a Monte Carlo simulation will work out. So, let's see this example. So the idea is let's imagine that we don't know the true value of pi, okay, of the pi, not the Greek letter, but pi, you know, the physical or the number pi, okay? And we want to estimate that. So we want to know what is the true value. So to do that, for example, we could take the geometry of a circle, because we know that, for example, the area is pi times r squared, right? And r is the ratio of square, right? So we could take this area of the circle, and then we say, well, the area is pi squared. So in some way, and this is the radio, right? In some way, we have pi there, right? So if in some way we can calculate the area, and we know the radio, then probably we can calculate pi in some way. So let's take a square or a quarter of this circle, right? And let's put a square around this quarter of the circle, right? Then we have r, and r is the dimension of the square. And then we have a quarter of a circle there, right? And then let's assume that we throw dart on this circle, right? And the idea is that you should throw this dart such that you end up in the blue area, right? Everything that is outside the area is something that you don't want. And then probably you're gonna do something like, you're gonna hit here, but sometimes you're gonna hit here also, right? And of course, as you get better, you'll probably hit more in the blue than on the white, but you can be really bad and be always on the white. It's random, right? Randomly will play a role, let's say here. So then, in this way, we could count how many darts ended up in the blue part, and divide it by the amount of darts that were in all the places, right? So if you do it for millions, or at least for thousands darts, you could kind of randomly cover the blue area, right? So you could say that if you count many darts that are falling in the blue area, you're kind of counting, if you sum it together, you're kind of counting the area of the blue area, right? And that should be equal to one quarter of pi times r squared, right? It's 1/4 of the circle, right? This is the area of the blue, right? And if you continue doing that and you are really bad and you are really random, then you also will cover the whole square. And that will be equal to r squared, right? R times r. So basically, if you count the number of darts that are in the blue area, and you count the total number of darts, the places of darts that are falling, and you divide it, you end up with, so this is canceling, 1/4 of pi. And then if you solve for pi, pi would be equal to 4 times the sum of the darts that were in the blue area divided by the total, with the total darts that were there. Okay, so that would be one way of calculating pi. So the only thing that you need is to define r, because in some way you have to, and then you have to run simulation of many different points in different areas, and then you will be ended up with pi in some way. So that's what you can do. So here is a picture where you have run it for 1,000 trials, and what we have is a variable that it can take x and y between 0 and 1, right? We imagine that the circle has a radius of 1 centimeter, right? And then we have a distance, right, a vector distance, which module will be r squared plus y squared, also the Euclidean distance, right? And then if this distance is below 1, you are in the circle. If it's above 1, you are outside the circle, right? So what you have to do is just count how many times you were below or in the border of the circle, and count the total number of points that you have. And with that, you can calculate pi. That's it. So that's a simple example of how to use Monte Carlo simulation or simulation to find a number that were unknown, just using this geometry. So the parameter here will be the geometry of the circle. Another example of using Monte Carlo simulation would be the example of, remember, if you have many people in the room and you want to find out which share a birthday, right? We did that many weeks ago, months ago, and the classical way was just to ask, and basically if there is one person in the room, there is 100% chances of not sharing a birthday because there is only one person. If there is two persons in the room, there is 364 over 365 chances of sharing a birthday, right? 365 are the dates of the year, and then you will have at least one that is shared. Then if 2 days are taken, then you have 364 over 355 multiplied by 363 because you have one less now over 365 and so on, assuming that they are independent, right? We did that exercise a long time ago. And then you end up with something like, if you have, I think it was 30 people in the room, around 70% chances of sharing a birthday. Now, another way to do this using Monte Carlo simulation would be that you take basically random number from 1 to 365, right? And let's say that you have 30 in the room, you take randomly 30, and you check which one are sharing the birthday. Then you repeat again. You take another 30, and you check which are sharing. And you do that for, let's say, 10,000 times, and then you take kind of an average, and then you could calculate the same probability. Then you can build something like this, where you can have the cumulative distribution of these randomly picking days, and look at which are sharing, and you will get something like similar, where you have 30 people, you end up a little bit above 70% chances of sharing a birthday. So another way of using simulation or Monte Carlo simulation to explain a phenomenon. All right, so basically that's it. Not much about Monte Carlo simulation. A note is that from what I have seen saying is taken from randomly means with all having the same chances of getting the number, right? From an uniform distribution. You could take it from other distribution, like normal distribution, Poisson distribution, whatever you want, and you will work the simulation as well. You will have some difference in the outcome, but you can actually use that too. So that is Monte Carlo simulation. It has something to do with random numbers. That's why we go to random walk. That's the only way that I can link these topics that are a little bit off the lecture. So random walk is something that you probably have heard about it if you have taken any chemistry lecture or some physics lectures. It's something that is when something is moving randomly. It has a random behavior, but in some way it's going to a direction, right? It will take some time to get to that point, but it's moving in that direction, but it's moving randomly. The way that I put it here is what is called sometimes the drunken man, right? The man that is drunk. It is not so drunk that he will fall asleep or pass out, but he still can know where the house is, so he will be going maybe from one street to another until he gets to home, right? And I learned here in Germany that sometimes happens on Fridays, especially in university settings. I have seen many random or randomia motion happening around here, which is very interesting to watch. Not that I am free of that. So the idea is, once you have this Brownian motion, sometimes you want to know the average distance that the man did, right? This is something that people are looking at. And sometimes they are also interested in where is ended up this person after any step. After walking some step, where he will end up. Maybe you are betting with your friends, he will be in the trash can, or he will be, I don't know, in some other place. So those are things that sometimes you are interested to look at. So how you can calculate that? Well, basically, if you have this MATLAB script, which is nothing really difficult, you can simulate something like a Brownian motion, and let's say that the person starts at 0, right? And then he will be doing something like this, and then moving from here, here, and then he gets home at the end. So, and then the last coordinate here are minus 41 and 12, and from 0 to that, there is a modulo of this distance, which is just a Euclidean distance, right? And that's why you can calculate it. So it sounds really silly, but it's important for physics events. This is just an example how you can actually walk around when you have to take it too many beers, but you can actually use it in a physical event. And basically, in this case, we have used it 2 dimensions, so x and y, and we have used a fixed amount of step size, so you always take the same amount of step, and the angle of the direction is also fixed, so it can be to the left and to the right, basically that. So how you can use this in physics? So something that is being very, some people is the diffusion rate, right, of particles. So you have, for example, how water diffuses in some medium, or how salt or whatever, when you have some materials in touch, sometimes you need to know if there is some diffusion of molecules from one place to another. And one problem is that calculating the average distance after n step is not so easy, right? And there was a solution done by famous Richard Feynman. You most probably know him, Nobel Prize, genius person, very funny guy, and very pro-education person. If you have not listened to his lecture, you probably would like to, because he is really a person that can make things simple, very complicated things very simple, and he is very nice to listen to. Unfortunately, he passed away, but he left us many things in physics, and one of the things was a shortcut to calculate this distance in the Brownian motion, right? He did a simplification. He just thought about 1D, so one direction, so one dimension, and the question was, what is the distance after n step, right? And the only assumption were that you always move the same amount of step. The size of the step is constant. It could be positive or negative, it could be one direction or the other, but it has to be always the same, which is called A in this case. So it's a constant A. The other assumption was that the module, so the distance, has to be equal to the average distance square taking the square root, right? This is, we'll see later why this is important. And the last distance that you get to after the diffusion or whatever you're doing is equal to the previous step, the distance in the previous step, plus the next distance A. Okay? So this is also important for the derivation. So then you can take, for example, the square of the last distance. So when we're talking about distance is, so if you start here, to the first one would be R1, to the second motion would be R2, and so on and so forth. It's the Euclidean distance of all our movements, right? So the last one, n to the square, will be equal to the previous one plus one step squared. And then you can open this binomial, right? And if you open the binomial, the middle part here has to be in some way close to zero in average, because you move as many A positive as A negative. So at the end it will cancel out. So we can actually move this to zero. And then we end up with just the previous one squared plus A squared. If you can see that it's a recursive function, it depends always on the previous one, then it will be equal to n times A squared. And with that, basically you can translate this from one dimension to three-dimensional just by having a vector now. It's not only a scalar, right? The distance is a vector now, and it can be in x, y, and z. And then basically this r square will be the sum of the average square or the square average in each of the dimensions. That's it. So with that, you can now calculate diffusion rate, for example, in a molecule of the molecule in some medium, right? And for example, here you have the formula, the physics formula of the diffusion rate or the diffusion coefficient, right? Each medium and each molecule, this medium will have a diffusion coefficient, right? And it's given by this diffusion rate times this parameterized of the materials itself divided by 6, that is also a parameter. So basically the diffusion coefficient will depend on the diffusion rate. And let's see if we can estimate it with random walk. So the diffusion rate has to be equal to the number of steps divided by the time that take every step, right? So you can say that the number of steps is equal to the rate times the time that took. And then you can put that back to our equation. And then if we do what Feynman say at the end, that R squared average is equal to n times A squared, we can actually plug here n, getting from here, right? And we'll end up with this formula, which is 6 times d, the coefficient of diffusion, times the time that took, and A, which is the step that you take every time you do. So with that, you can define the final distance of a molecule diffusing in a medium, right? Because you only have to measure how long it took to move, right? So if you have the time that it was diffusing, then you will know the distance it will end up this molecule, okay? And then you can define the diffusion length, which is just the square root of that, and that's a parameter that describes the diffusion process in a chemical process or in any thing that you are looking at. Of course, this 6 can be changed by more complex formula where it's not only a factor, but it's a geometry factor, and will depend on the material's properties, and then you can plug that there, and you can even simplify it to 1 in some materials, and then you can have a very simple formula of the diffusion length by just having the diffusion coefficient multiplied by the time squared. So the take-home message, I guess, is you can use random walk to as a physical event, right? That it can be measured, and it can be measured the distance that anything is moving, and you can estimate where it would end up after some steps. All right. So Monte Carlo simulation and random walk kind of in some way related to each other because it's random. Next topic of this lecture is sample size estimation that I want you to just touch a little bit because it's an important topic. If you want to sound that you know about statistics and somebody comes with you with a problem of statistics that they want to compare means or whatever, you have to ask, have you calculated the sample size? And then the person will open the eyes and you will not know how to answer that. So if you want to sound smart, and some people just ask that question, and you will see that people get nervous because it's a topic that is very important. Basically, if you don't have the correct sample size, whatever you are doing is wrong in theory, because you have to have enough data to claim what you're claiming. If not, you're just guessing. And that's a topic itself. In calculating how many samples, how many points you need in each group is not easy for methods that are a little bit more complex than ANOVA and t-test and so on. Okay? It requires to know a little bit about the phenomenon before. It requires about know the difference, that you have an estimation of the difference that you would like to see, and in some way, sometimes it becomes really complicated, and people just do run a rule of thumb and say after 10 samples is okay or so on. Okay, but here we try to give us some theoretical framework, if you want to call it, to this. And basically, you want to know, if you want to know the probability of something to happen, you want to know how many points you need to say that this probability is probably true. It's not just the case that happened. And we can start by, you want to estimate the probability by the Laplacian probability, right? So what's the number of outcome related to what you are interested in over the total number of outcomes, right? Going back to many lectures before. So you want to estimate this p hat, right? So this p hat is what you want to know. And you want to be sure that this p hat is correct within some confidence of interval, right? Or intervals of confidence. And this will be defined always with an alpha, that our alpha usually is 0.05, remember? And so our p estimate will lie between plus the confidence interval and minus the confidence interval, which will be given by some critical value, right? If you remember the lecture of confidence interval, that was the idea. And it was something related to this formula. We divided this critical value by the number of points that we have, n. And we would need, in this case, for example, is, you can do a binomial distribution as Bernoulli experiment right here. Then it will be p times q, or p times 1 minus p, right? And then you will have all that you need. This is the standard deviation, remember? And with that, basically, you have the true p in the upper and the lower part. It will be in some way close to our estimated p times this in confidence interval. And then this is where we're going to be, around this part. Now we have n in some way there, so we can start deriving or trying to solve for this n to know how many points you need to be within this confidence interval that you want to be. So the first thing is to calculate c. C could take as inverse of 5, remember? Alpha, something that we're gonna define, so in this case 0.05. So for alpha 0.05, our C in the table of standardized and normal distribution is 1.96. So, and then you have the length of the interval, L, which is this guy minus this guy, or the other way around, this guy minus this guy. So it will be 2 times the confidence interval on one border than the other, right? So, and of course it's going to be some estimation, that then there's going to be some error, and you want to be bounded this error by 2 times epsilon, epsilon meaning anything that is very small, in this case 0.02. So this is basically what we need to know to derive N. And if you solve it from here, you end up with some estimation of the number of samples that you need, depending on our P, and depending on our critical value, which depends on alpha, and that's it, and epsilon, in this case, how much error you're going to have. If you don't know P, which probably you don't know, that is what you want to estimate, you can estimate the worst case. In this case, since it's a binomial distribution, you say that P, we estimate as 0.5. So 0.5 times 0.5 is 0.25, okay? And then you plug that there, and given C and given epsilon, you can estimate the number of points that you need on the group. And that will be, for example, for an alpha of 0.05 and an epsilon of 0.02, you need 2,401 points. If you know better P, and you, for some reason, you know from some other experiment that is exactly 0.2, then you plug 0.2 here, and you need less data. That means that you already know something about the experiment or the outcome, so it makes sense that you don't have to collect as much data as when you don't know anything about the experiment. So this is really simple sample estimation. There are much more complicated methods to calculate depending on what you want to do. All right, so last topic that I will, let's say, roughly touch here, last topic of today and last topic of the year. Oh, the semester, sorry, the year for me, because I don't repeat this in the summer semester. Errors from a stochastical point of view, not from mistakes like I marked here. So let's say that you have collected some data, you measure resistors values, the resistance values of a resistor, and then you know that there is some true value. Let's say that it's 5 ohm, and you always collect 4.99, 4.75, 5.1, and 1. Right? So there is always an error. Okay, there is a delta. This error could come from 3 sources at least. One is the blunder error, which is something that should not happen, that you measure it with incorrect tool to measure. Like you are measuring weight with, I don't know, you're measuring your weight with a scale for trucks. That's not correct. That's probably give you a huge error. And then you have systematic error. Systematic error will be something that is biased. So there is an error in the machine that you're measuring that is always giving you an offset, for example, that's giving you 0.1 more than it should be, always the same. And then you have a stochastic error, is the topic that I want to approach today. And this is something that happens by nature. So for example, the resistor, depending on the temperature of the resistor of that data you're measuring, might be higher or lower. And this is random, okay? Because the temperature in the room is changing randomly, okay? So that could be a source of stochastic error. So let's say that we measure resistor and that the true value is around 205 ohm. Then you have a distribution of measurement that could be normal or non-normal, could be anything. In this case, let's assume that it's normal. And you want to know how the sum of all these measurements actually distribute. Okay? That is the sum of the error. Then you can approximate, as always, by the normal distribution, your error, depending on how many data. And then there's going to be a true view, a true value that should be measured, and our measurement will lie on the left or the right of this true measurement that you will do. Nothing crazy. And there will be some dispersion of our measure through this mean to the left and to the right. So depending on how spread it is, how our measurement spread it, we will cover with 1 sigma 68% of the point, with 2 sigma 95% or 99%. Okay? So it's important that our sigma or our spread of the measurement is as smaller as possible, so that we can cover all of our measurement in a small interval. So, what is the idea? So the idea is so you will not know, of course, if you are measuring something, you could know, but you could also not know this mu, right? And you want to estimate it roughly so that you are falling within the mu that you are measuring, right? So you can get a suitable mu for that. That is the accuracy that you will look at the measurement. Calculate error propagation. That it could be, for example, the resistor is placed in a board, and then you are measuring on the board, not directly on the resistor. Then you will have the error of the resistor, the error of the board that is in some way producing noises, whatever, and then the error of the measuring tool, so that you have propagation of the error, right? And then you can fit the normal distribution to that. So the best estimation of the mu will be always, as we know, is the average, arithmetic average. And then the best estimation of the variance, or the standard deviation, would be our formula for the standard deviation, right? Nothing new. And then that's what I say. Our measurement in average would fall in some way to the left or to the right to this true mu, which is normally distributed, right? And basically, again, we can define confidence of interval, or intervals of confidence, sorry, to the left or to the right to this mu. And with that interval of confidence, we actually can, in some way, give the precision of how the measurement is. Nothing new here. In this case, we are using student t-test distribution. So we have a t-statistics critical value to the left and to the right. And with that value and the standard deviation and the number of samples and the estimated mu, we can build our distribution. There's going to be always a table for that, because this is T distribution, so we have degree of freedom, and we have our gamma or alpha. Gamma in this case is 1 minus alpha, right? And basically, that is what we do. So before we just define the error itself, just a note, you probably have physics one time in your life. You know that there is an absolute error, so the true difference between the values and the true value, right? And this has the same dimension that the true value, so it has the dimension x. Then you have the relative error, which is the absolute value divided by the mean, or the true value that you want to look at, and you have no dimensions. And then if you multiply that by 100, you will have in percentage this error. Nothing really steep. So let's have an example. Let's say that you're measuring the swimming period of a circuit, okay? And it gives you some measure of time, 1.254, whatever, 1.258, and you want to estimate how is your true mean on that respect. So you take the average and you take the standard deviation, the first thing that you do. Then you go and calculate your confidence of interval of confidence with n equal to 6, 1, 2, 3, 4, 5, 6, standard deviation, and for an alpha of 0.05, it means a gamma of 95%. You go to the table and you get the critical value as 2.57. Then you multiply all these together to get your confidence interval. So that would be plus minus this, right? So to the left will be minus, to the plus will be minus. So your mean true mean will fall within this interval, and you describe that the true measure with an error of 5% given our alpha is 1.253 plus minus 0.006, and that's it. Really silly thing. I made 3 or 4 slides to say something that you probably have guessed, that you have an stochastic error, that you can have it normally distributed, there is a true mean, and there is some dispersion around the mean, and that's what we're describing here. That's all. All right, with that, thank you again to be here. Thank you for the ones that are listening. I only can say good luck for the next steps. So I think at least you should know something about what a distribution is, what a probability is, what a distribution is useful for, right? How we can describe real data with distribution, and how we can compare distribution to solve questions or answer questions, okay? There is much more to say about this in statistics. This is just an introductory talk, lecture, but there are many other levels of statistics that you should learn if you're interested. Next week, we cover strictly the exam, so you have a good sense of what's going on in March. And I think you should be fine if you have followed me and you have made the exercises. Usually it's fine, so nothing crazy will pop up there. But we'll talk about that next week. So thank you today. You can go now grab another coffee, and thank you for being here. And many of you have been in all of the lectures, so thank you so much for the attention. All right? So see you next week then. Ciao, ciao.